Okay, so after about 20 minutes or 30 minutes or so, our platform studio image has been created. Um, this is the hardware side of a design. The next step is to be able to write software. Part of the whole reason that we use the platform studio is so that we can have a software interface running on the microblaze processor, or if your chip has an embedded processor, but be able to run C code on that processor. So in this video, I'm going to show you how to use the SDK part of the Xilinx Platform Studio to integrate your programming language code with the hardware part of your design. We're going to start with a XPS project that I have open. This is the same project that I demonstrated in the previous XUP v5 setup video. Is generated. As we can see, the bitmap has been configured. The next thing I've got to do here is take this design and build a software project with all of the definitions. In particular, what we're after here are all these definitions about where things live in memory. So I'm going to go ahead and export this design to the SDK. After some chunking and some churning, what should happen is what is essentially Eclipse will start up. And what you'll have here is an Eclipse version of your package. And the SDK should have created a hardware platform that describes your hardware image. This is useful not directly for our stuff, but to create a board support package. The board support package is the linkage between all of these different hardware drivers and what will become our code. So the first thing I'm going to do is I'm going to go to Xilinx Tools, and I'm going to, I guess I'm going to do a new other. And I'm going to go to Xilinx, right there it is, Xilinx Board Support Package. And I want to make sure that the right hardware platform is selected. It is. We could give it a name. For instance, we could call it Demo. It doesn't matter. The choice of the kernel here is kind of important. If we just want to write C code that's going to run directly on the microblaze processor, standalone is probably sufficient. It's going to give us the closest environment to what would traditionally be a microcontroller architecture of the two. XIL kernel gives us some very lightweight kernel options. For example, the ability to have multiple kind of like processes running, but it's not really going to be giving us a full-up Linux kernel or something like that. Let's just stick with standalone and hit finish, and the wizard for the standalone option comes up, and here we get to pick what libraries do we want to include in our design. So our design is not using really anything all that fancy, so I'm going to leave all of these off. The standalone does use some configuration. If you want to connect to your board, if you've included standard in and standard out, you want to be able to do, say, printf and fgetS. If you want that to go to the serial UART, then to do that, you need to make sure that standard in and standard out are connected to that device. On the other hand, if you want them to show up down here in the terminal in Eclipse without having to plug in a serial port, then you can choose to use the debugger port, the microblaze debugger. And now what's going to happen is, as long as the USB is plugged in, when this program runs, any terminal input and output will be directed through the JTAG port and displayed here in the terminal. I'll go ahead and leave that set so that I don't have to have another cable plugged in. My desk is pretty hectic. If you were going into a production kind of thing and you really wanted this thing to be plugged in over a serial port and you didn't really want to have a debugger connected to your board, then you probably want to leave these as you are. These are the default drivers as far as the board support package is concerned. These are the default libraries that will be included in the support library. And finally, any special flags we want to make for the processor. So we want to change, for example, maybe change the optimization flags or anything like that. Yeah, we're pretty good here. So I'm going to hit OK. We'll watch it build down here. And we want to make sure that there's no warnings or errors that are displayed. Okay, so at this point we have a board support package. So in other words, we have from XPS we have a hardware platform that's created a link from the actual bit stream and all the different Verilog and VHDL modules. Those definitions are encapsulated here in this hardware platform description. We have a standalone BSP, which is our board support package libraries, which we can now use to build our executables around. So I'm going to do just that. So we'll make a new other, and we're going to do a Xilinx C project. If I just do a generic C project, I have to do a few extra steps. So in this case, we're going to do a Xilinx C project. We can choose which one of these we want to use as a template. I'll just do Hello World. We'll do Next. It's asking what our project name wants. If we want to use an existing board support package, which we do. And at this point now, it's actually created a sample C project. It's compiled it, and it's ready to execute. Let's take a look at what it did, first of all. So we see that it included platform.h, it called init platform, it called print hello world, and it called cleanup platform. And if we take a look at this, we see that platform.h is doing this init platform, cleanup platform, platform.c does a whole bunch of initialization functions. So when we call init platform, it's turning on the UART if we're using them and enabling caches. Actually, if you think about this, we didn't use a cache and we're not using the UART, so there really isn't much for this to do. But nonetheless, we should be able to run this program. So, okay. Now, for the last time, we should try to program the FPGA. Okay, now it's actually programming. So nothing drastic is going to happen here because this is just the boot loop that it's running. Now I can go and run my program. So I'm going to go here to run config. I want to choose the new Xilinx C, C++ ELF. This is the executable and linker file. There's our hello world. I'm going to tap on run. And it says standard I/O is not connected to the console. What's going on here? That's a common error. And what happened was, even though I set up the BSP to have standard in and standard out go to my MDM, I didn't actually select it here. So we're going to choose standard I/O to console, and we're going to choose JTAG UART as our port. We're going to hit run, and sure enough, hello world. See? Yay, hello world. So there is the basics of setting up a Xilinx SDK project and getting in and being able to program in C language. Just as a really quick example of one other thing we can do here, I see that I have LEDs. I have my LED 8-bit, And one thing we can do is we could actually go and look and see how we can connect to these things. So I'm back here at system.mss. This is the board support package display. And one of the nice things they do here is they give us examples of how to talk to the existing BSP libraries. And so, for example, we can look at XGPIO example source, and here we see that we can make some function calls. First of all, let's find make sure we include these two files. I find that as I poke around here, I save my files an awful lot. And it says here we were going to want a status variable. And really the thing we're after here is we want to call that. Now, if I continue following along our example, the GPIO variable is actually an XGPIO. And we'll pass that in. And what it's really saying is here, I don't have that. But I do have an X parameter, LED, 8-bit, device ID. And that device ID, let's go back to our sample. That device ID is how this library function initializes the GPIO driver for that. We want to set the direction for all signals to be inputs except for the LED output. Really, we could just do X GPIO set direction, and it's going to be GPIO. Channel is going to be 0. Actually, we'll do the bottom 8. So the 8 bits will be 0xFF, and the direction mask is going to be output. So we're going to drive the first 8 bits. We'll do our hello world still just to make sure things are working, but now forever we can do a while true. We go back to this example. Essentially we can read the existing port. So that's reading the old data, and if data of 0 is equal to 1, we're going to make data equal to data XOR 0xFF. Actually, we can do and we're going to do that. So if the lights are on, then we're going to AND this with, oh yeah, if it's on, we'll XOR it with 0xFF. That will turn them on. And else, data is equal to data or 0xFF. So we can use an XOR mask, and here we can use an OR mask. And then we'll do XGPIO, discrete, right. And we're going to again do GPIO. In this case, we're going to do 0xFF. And we're going to do data. And then we have to delay. And typically the way you delay on these things is just an infinite for loop. Well, not infinite for loop, obviously, but a loop. So let's pound define LED delay to some large number and then delay. All right, we'll use an AND mask to get just the lowest bit. If that lowest bit was set, we'll clear it, and if that bit wasn't set, we'll set it. And then we'll write that value back to the GPIO lines. So theoretically, if I run this code, we have an error. And to debug an error, this is really slick. We'll stop this guy. I'll put a breakpoint in my code, and now instead of running, I'll go to debug. And believe it or not, it's actually going to run on the board, but it's going to let me single step through my code through the normal Eclipse user interface, which I think is really cool. So we're going to call that. We'll step over that. We'll step over that. And that turns out to be a fail. Actually, this is the one that's going to be the fail. That needs to be a 0 or a 1 to indicate which bank of the GPIO module we're using, which in our case, everything is going to be 0. Sorry about that, guys. Doesn't explain why that failed. But we'll try it again. Okay, so we can step, step, and something there is truly unhappy. So let's try one more run here. All right, so we'll step. And this time we'll step into this function. So we're definitely getting into I see. Channel is not 0, it should be 1, 2. well, if nothing else, this is a good demonstration on how these tools actually do help you do some debugging. All right, so let's see where we get this time. Yeah, we still haven't. Oh, nope, we got to the print statement. And we get to our read. We'll turn on those bits. We'll write them back. Oh, and they all turned on. I just looked over at the board, and now we'll run. And I'm watching them blink on and off. So we used the debugger. Everything worked out just great. Let me go back to my C++ view. Take a look at our code one more time. This is using the built-in GPIO drivers in order to program the board. This isn't the only way to do what this program needs to do. For example, I will demonstrate this very quickly. Instead of doing it with the Xilinx tools, you make a volatile int pointer, and we'll make it should be unsigned int. And this should be an unsigned int. And that's going to be xpar LED 8-bit. In this case, instead of going for the device ID, we're going to go to the base address. And so now I have an integer pointer pointing to the very beginning of the memory where this device lives. And we'll make one more int count is equal to 0, and for count is equal to 0, count is less than some big number, count plus plus. There's our delay statement again. This all needs to happen inside a while loop. And the only other thing I need to do is actually to flip the bit. And in this case, GPIO. So the pointer, I want to dereference the pointer. So if GPIO ampersand 0x1, if that's true, then we're going to do GPIO XOR equals 0xFF, else GPIO 4 equals 0xFF. And so now we'll turn on the bits. And these all need to be dereference pointers. All right. So now this code is using C language's built-in pointer manipulation. And since we're doing memory mapped I/O, changing the pointer values is doing the I/O to the device. If I run this code, the light should blink. Or else I have an error, which is a good possibility. All right. Well, we could go and debug and see where we've gone wrong. But that's the general strategy. So you can either use the built-in functions. Remember, you can get the documentation and examples on those from this screen, and it'll pull up a web browser, or else we can go and do it by hand manually by using C language's pointers. The one trick to remember is we've got to use the volatile keyword to modify a pointer to make sure it doesn't get optimized by the compiler, or else if we try to read from this pointer, if we just wrote to the pointer, it will think the value is still in a CPU register and it won't know to continually refresh it. But that's the connection between the hardware and the SDK. I hope that helps. Thanks a lot. Bye-bye.